In this image, you can see that there is an agent that interacts with its environment. So that's the key and core concept of reinforcement learning. We have an agent that can take actions, make decisions, and then receive feedback in the form of rewards from its environment. You can see here the letters S, A, and R. So these denote state, action, reward, which means that the agent can change states. It can be in different parts of the environment. And in a changing environment, the agent can learn to take best possible actions. How does it learn this? Well, it's rewarded for the environment for taking better actions. Eventually, it will learn a policy for all these states and actions. You can see here it's denoted as letter P. The rewards usually come from the environment, so the agent can observe changes in the environment and figure out whether it achieved the goal or not. But this doesn't have to be the case. The agent can also have its own internal reward systems. Very important is that this is one of the rare approaches where an agent can learn by interacting with its environment. It can learn from trial and error, similar as us humans do, and it can be very effective at doing that. Reinforcement learning is one of the most effective AI approaches. It actually requires zero data to start with, and you can train a robot to navigate a lab or become an experimenter in a lab. You can train an agent to play a video game, all starting with zero data. Now, there aren't many AI approaches for which you can say that. To differentiate this approach to a typical AI approach that we are using today, a lot of them are supervised in their nature. Uh, in supervised machine learning, we have past data, usually a lot of past data, which is not easy to collect. There needs to be a lot of pre-processing and working with the data. And we also need to label. For example, if this was an image recognition system and we had 100,000 images, 100,000 images would need to be labeled for this AI system to learn. And to differentiate that from reinforcement learning, where we actually don't need a lot of data, we actually teach the agent, or the agent will actually teach itself by interacting with it with its environment. And it can be highly specialized, not only to make predictions, but also to take actions and make decisions. This is another very important feature of reinforcement learning, which differentiates it from many other similar approaches. Eventually, as I said before, the agent will learn a specific policy. This policy will mean that for all those changing states, we're going to learn the probabilities, which we call the transition probabilities, which is the probability of going from one state to another. And then as the agent changes these states, it also learns which are the best actions to take, and eventually which will be the sequence of actions that will lead to solving a specific problem or achieving a specific goal. The easiest way to think about reinforcement learning and how an agent can, for example, play a video game, learn how to play a video game, is to consider a maze. So a maze where the agent would have a starting point and the end point where the agent needs to find a solution for the maze to go out of the maze. And you can see here that it's not about making predictions. It's not about making one prediction or one action. It's about actually making a sequence of actions, and that sequence of actions, that pattern of actions, would actually lead to solving a maze, eventually going out of the maze. So from now on, I will be considering mostly sequences of states, actions, and rewards when speaking about reinforcement learning, rather than making a single prediction or anything single in terms of the actions or rewards. Another very important feature is that the agents should be able to solve problems in a dynamic and changing environment. So if we teach an agent to solve just this maze, and then we give it another maze or a set of mazes, it's not going to be able to solve them unless it's trained to find universal patterns, universal decisions, universal actions to take and solve any maze or any state that it's in. So that's why it's important when training reinforcement learning models to have large amounts of different variations and states in the environment so that your agent can learn to find solutions in any different situation, not just in specific ones. Now, another important aspect in reinforcement learning is that we have no labels, which means that the rewards usually come later. They usually come once the agent solves a specific problem. In this case, we have a robotic mouse, so it would need to find the way to its reward, the cheese, and the steps in between and the actions it took in between would not be rewarded probably initially, right? So we need to find a creative way to actually reward the agent backwards in time. And that's called a time delayed reward in reinforcement learning. We'll be exploring that more on that shortly. Before that, let's discuss some of the terms and principles also used in reinforcement learning. One of them is called the Markov decision process. Markov decision process is essentially related to what I was talking about before for the maze. It's not a it's not one prediction or action. It's actually a sequence of actions, sequence of states, and then we also need a sequence of rewards later. So we have SAR, and so on. They're repeated. So we have a sequence of all these, which actually make the Markov decision process and making decisions easier to learn for the agent. Another feature which is very frequently used, not always, but very frequently, is called the Markov property. Markov property means that any future reward, any future state, is dependent only on the current state. And that's how I'm going to learn, and that's how I'm going to take actions. So you can imagine a situation where I'm driving in a traffic. So how am I going to make decisions? Which turn to take? Where to go? I'm going to look where I am right now. Where is my goal? Where do I need to go to? And then I'm going to make decisions. I don't care where I was yesterday or 5 days ago. I care where I am right now. And that's how I'm going to take actions and learn. So the same principle can be applied to agents. There are other principles, but this is one of the core ones to learn. Then another important aspect, which we also saw in the mouse maze example, is the time delayed reward. The time delayed reward and rewards in general are some of the most important aspects in reinforcement learning. The better the reward system, the better the reinforcement learning system. It's one of the core and key components. Now, it's not easy to reward an agent effectively if you have a reward only at the end of the game, only at the end of the maze, or at the end of any problem the agent is trying to solve. So you can see here that if we start, you can think of a maze where we have S0 initial situation, and then the agent takes different turns, action 0, and then because it didn't yet reach the reward, it will receive 0 reward. So the R0 will be 0. And the same would be for a number of rewards, maybe 10, 15, 20 first actions would not be rewarded at all. All those rewards would be 0. The reward would only come at the end of the maze, which is R3 here, hypothetically. So the problem is, how do we assign the credit to the actions that led to this reward? Previous rewards are 0, so we clearly didn't assign them yet, and we need a creative way to do that. So the reward comes later, and we need to propagate the reward backwards in time to reward the actions that led to the final solution, to the final solution of the maze, for example, in this case. There are two main ways we can make the agent learn by propagating information backwards. One of them is called backward induction. So in backward induction, this propagation of rewards backward in time happens in one pass, all at once. So basically, we have no rewards at the beginning. At the end of the maze, for example, there will be a reward. And then we figure out, hey, this is the reward. We're just going to send and propagate information backwards in one pass and figure out which actions led to this reward. Another way is to use a more incremental approach. So we will be sending information backwards in time in a similar way. However, when the agent learns something in game one, for example, in game two, the agent would be trying to estimate at every state whether its future reward will be worse, whether it will be more probable or less probable to reach some future reward. So we have a combination of incrementally sending information backwards when we reach the end of the maze, for example, but we also estimate at each step whether we are in a good position, whether moving from state one to state two will be beneficial for the agent. There are so many creative ways we can make this system better, and the reward system itself is usually a defining factor of how well will the agent learn during the interactions with the environment. Another very creative way is to add intermediary rewards. So we could add smaller rewards, for example, at S1, S2, somewhere in the middle, and we could have a larger final reward at the end of the maze. And the agent would not learn only at the end, it would also be able to pick up these smaller keys, smaller rewards somewhere in between. I will be mentioning this more on a chess example, which is maybe a better example to explain the intermediary rewards. So the key difference there is in backwards induction, we reach the final reward and the reward is propagated backwards in time in one pass. So it's a very simple system. In the temporal difference approach, we propagate information incrementally, also backwards in time, but the agent can also estimate what will be the potential reward in the future if it's in a specific state or if it moves in some other state. So these are the two approaches that we were mentioning during the previous slide. When training the reinforcement learning models, it's very important to understand that these models are trained in steps, not like other AI models where we basically have iterations. So for every iteration, the model makes a prediction and then we backpropagate the information to see if the prediction was correct or not. In reinforcement learning, we have these steps which are more complex than single iterations. So in every step, we have SAR or state action reward. And very importantly, we have a transition to the new state. So this is a single step. You can imagine an agent observing where it is in this video game and then taking the action, for example, jumping onto a brick and then it changes and goes into a new state. It can be rewarded or not rewarded in the meantime, and this would be one step in the sequence of steps that the agent can make. Now, a larger sequence of steps would eventually lead to either a game over, where the agent would lose the game, or win. We would want the agent to win, but even if it doesn't win, the agent can also learn something from a game over, from losing the game. It will learn what not to do. You can imagine an agent winning a game and then also sending information backwards in time through the ripple effect that I was mentioning before. So if it wins the game, it's going to go back in time and evaluate all the actions it took Like it jumped onto the brick, it collected a coin, it collected a star, it avoided a pit, and then eventually that led to winning a game. So uh, this is very important to understand. If you start training reinforcement learning models, you will be seeing these steps, and then you will also be seeing the episodes. So the episode is actually the agent playing one game and winning or losing, and the episode is composed of these singular steps. Each singular step is composed of state, action, reward, sequence, and transitioning into the new. Another cool example is snake game. So you can teach an AI agent to play a snake game. The reward is an apple that a snake needs to eat, and there's a similar architecture as for the mazes. So here's just an example of a snake game agent that I trained to play games. You can see it's very effective. It's achieving solid scores, and it's playing really quickly. So that's another AlphaZero by Google DeepMind, where they trained chess agent by playing, self-playing a lot of games, millions of games potentially. It has almost unlimited potential in terms of learning, and it became so powerful that it beat the world champions in chess. And all was done with zero data. So zero games of data. That's probably why it's called the AlphaZero, if I understand well. And again, just one of the great examples. Now, since we're here at the chess, it's a great opportunity to discuss the rewarding systems. So we can reward the agent at the end of the game. For example, two agents could be playing a chess game, and if one agent wins, that's a reward for the agent, and it can go back in time, see which moves did it play, and then reward them. However, we can really model the rewards better, so we don't have to reward the agent only at the end of the game. We can also have these rewards that come in between. Like every time an agent takes opponent's piece, it can get a reward. Or every time an agent resolves a specific situation, such as the one on the top left, it can also get a reward for resolving that situation. So we can create these intermediate rewards, which will make it much easier for the agent to learn. So we don't have to only reward the agent at the end of the game. Uh, the creativity very often comes from how do you create these intermediate rewards in reinforcement learning. Finally, something to consider at the end of this video, which will probably be explored further in some of my next videos, is the deep reinforcement learning. So deep learning has become so powerful today, and there are so many use cases. So combining deep learning neural networks with reinforcement learning is one very, very powerful combination. So I would suggest for anyone interested in this field to explore deep reinforcement learning. Another thing to explore, another field to explore is control theory. You will see that in reinforcement learning, it's a lot about learning, teaching the AI agents how to make best decisions, navigate different environments, make best actions based on the changing environment. So control theory is a lot about if my environment is changing, how do I keep the best control? How do I make the best actions? So that's definitely another very important field. So far in this tutorial, we've discussed examples from the gaming industry using the reinforcement learning. However, reinforcement learning is used in various other fields as well. Starting from the digital AI space, where we have large language models being fine-tuned using reinforcement learning. One of the most important use cases of reinforcement learning is in agentic AI. You've seen from this tutorial that at the core of reinforcement learning is an agent. So one of the obvious use cases is in agentic AI. We can train AI agents to interact with their environment better. If you study agentic AI, you will see that in agentic AI, one of the most important aspects is the environment of the agent that can perform a specific task or use specific database, use specific tool set. So reinforcement learning is one of the most effective ways to train the AI agent to be better at using this environment, using the data sources, using the tool sets better, especially the sequence of using different segments of the environments. So agentic AI is definitely, in my opinion, one of the core use cases of reinforcement learning. And then going all the way to physical AI, where we have self-driving cars, which are, again, in most cases, trained using reinforcement learning in combination with some other approaches. We have robotics, one of the most interesting and promising fields in AI, where robots can physically interact with their environment. And again, using reinforcement learning, they can be trained to be much, much better at that. One great example is having a lab robot companion or assistant, lab robot technician, which can interact with a lab, with instruments, and then learn to be much, much better at that using reinforcement learning.